Good afternoon, everyone. My name is James, and today I'll be presenting my project titled Adversarial Robustness of AI-based Threat Detection Systems. This work was completed as part of the Advanced Computer Security System course under the supervision of Professor Kia. The goal of this project is to understand how adversarial attacks compromise AI-based intrusion detection systems and how defense like adversarial training can strengthen them. Here's the outline for today's presentation. I'll start with the project introduction, problem statement, and key insights. Then I'll cover background, related work, and limitations. After that, I'll walk you through the design implementation and methodology. Finally, I will show evaluation results, conclusion, and future research directions. AI has improved malware, phishing, and intrusion detection, but small, careful changes in data set known as adversarial attack can cause the model to misclassify malicious traffic as benign. Most adversarial research focuses on image datasets, and very little work evaluates adversarial attacks on network intrusion datasets like CICID as 2017. Defense strategies like adversarial training are rarely applied in cybersecurity context. This creates a real risk to the confidentiality, integrity, and availability of critical systems. Um, AI-based ideas models show excellent clean accuracy, often above 97%, but literature shows adversarial attacks can reduce accuracy by 20 to 60%. This means clean accuracy alone is misleading. We must also measure robustness. A system that performs well but collapses under manipulation is unreliable in world security operations. According to IBM 2025 cost of data breach report, the global average breach cost is around 4 to 5 million, and cybercrime losses across industries are in trillions annually. As organizations adopt AI-driven security tools, attackers as well increasingly target the models themselves. Therefore, improving adversarial robustness is both technical and economic imperative. Before discussing adversarial attack, let's briefly review how ideas evolved from rule-based systems to machine learning-based systems. Early ideas systems use static signatures and rules, like if an IP scans many ports, raise an alert. These systems were good for known attacks, but failed against novel or slow stealth attacks. Attacks could possibly bypass rules by modifying behavior patterns. Machine learning have changed the landscape by learning patterns from data instead of relying on fixed rules. This made detection faster, adaptive, and better suited for complex threats. However, machine learning models introduce a new attack surface, that is adversarial manipulation. Adversarial attacks subtly modify input data to fool AI models. In network security, this may look like small changes in packet timing, payload size, or flow statistics. Two attacks evaluated in this project include FGSM and PGD. Uh, There are so many proposed defenses mechanism for adversarial attack, which include feature spacing, detection of adversarial inputs and symbols, and adversarial training. For this project, adversarial training and ensemble is the primary defense that will be evaluated. Most adversarial machine learning research is image-based, and a few weak start attacks on network traffic models. Even fewer evaluate defense effectiveness in cybersecurity settings. This project directly addresses those gaps. The main objectives of this project is to build a baseline threat detection model using CICIDS 2017 datasets and generate FGSM and PGD adversarial attacks, and then apply adversarial training and ensemble as a defense mechanism. And after that, we evaluate and compare model performance before and after the defense, and then provide a full reproducible open source pipeline. Challenges. Some of the challenges in this project include the CID dataset, which is very large and has imbalanced uh, dataset, requiring carefully pre-processing. Another challenge in this project includes overfitting on high dimensional network flow features, and PGD generation is also computational expensive, and also a realistic epsilon value must be chosen to reflect the actual attacker constraints. This figure here summarizes the full pipeline that will be used from data pre-processing, baseline training, adversarial attack, adversarial training, and evaluation. The idea is to measure how strongly adversarial training improves robustness across attack types. The methodology that will be used in this project include stratified sampling to prevent class imbalance issues, and features were imputed, scaled, and constant columns were removed. Training stability improved using early stopping dropouts and L2 regularization. FGSM and PGD hyperparameters were tuned for realism. In this project, we used multi-layer perceptron with two hidden layers. This architecture works well for tabular intrusion data. The model uses dropout and L2 regularization to prevent overfitting. The baseline is trained on clean data only, and early stopping prevents overfitting, and checkpoints were used to ensure reproducibility. After training, we evaluate how both FGSM and PGD affect the baseline. This represents the first order and iterative gradient based attacks. A baseline model attack evaluation measures the model accuracy under adversarial conditions. And the training procedure includes model training using hybrid datasets that contains clean samples and PGD generated adversarial samples. And after the model is trained, we measure the model accuracy. And then evaluation. Uh, the baseline performance achieved a model accuracy of 97.63% and false negative rate of 3.96%, indicating strong detection of malicious traffic. This established a high performance and but attack on vulnerable baseline. The model performs well in normal conditions, but the high accuracy shows the ability to detect malicious traffic. However, this does not reflect the real world adversarial conditions. The sharp decline of around 12 to 14% revealed that the baseline model is highly vulnerable to manipulation. With a Pilson of 0.05, the FGSM drops accuracy from 97.63 to 86.54%. This shows that even a single step attack can significantly compromise the IDS model. On PGD, it is stronger and iterative, and dropping accuracy to 45, 85.38%, and the attack success rate climbs to 14.62%, showing a deeper vulnerability. Um, Then interpretation and insights. These results align with Goodfellow and Madri's findings. High accuracy model can still be extremely fragile, as the real-world attacks can exploit this fragility to bypass AI-based security systems. Adversarial training mixes clean and adversarial examples during training. This improves robustness by 7 to 8% with almost no drop in clean accuracy. This matches the literature as the strongest defense. And then ensemble method helps slightly on accuracy but poorly under adversarial noise. The model disagree much under the perturbation, reducing the robustness. And then comparative evaluation and the defense effectiveness. The baseline performs well on clean data but collapse under attacks. Adversarial training significantly boosts robustness across FGSM and PGD, and Ensemble provides limited benefit as shown on the figure shown there. So the key takeaways from this include the adversarial training is overwhelming the best defense mechanism for IDS systems, and Ensemble is less effective and also reduce model accuracy. The baseline models remain extremely vulnerable without defense. Conclusion. AI has strengthened intrusion detection systems, but adversarial attack remain a major threat. This project fills a gap in evaluating adversarial robustness on real IDS data. Results shows that adversarial attacks severely degrade performance, but adversarial training restore robustness. Baseline results show that FGSM and PGD attacks significantly reduce the detection accuracy, exposing risk to security critical systems. A full pipeline, the baseline attacks and comparative provides a reproducible open source framework that future researchers and cybersecurity practitioners can build on. And then future work includes adding more data sets like a UN SW and malware data sets like Ember. We also plan to test strong attacks like CNW and Deep4. And finally, building an automated robustness testing pipeline. And that would enable continuous evaluation.